All right, so here is a example with a real object. So we have in the figure below a particle of mass m equal to 0.67 kilograms is a distance 23 centimeters from one end of a uniform rod with length L equals 3 meters and mass equal to 5 kilograms. What is the magnitude of the gravitational force F on the particle from the rod? So with this problem here, because we have a real object, we can't use that force is equal to G times mass 1 times mass 2 over r squared, because mass 2 in this case, which is going to be the mass of the rod, it's not a point mass. So since it's not a point mass, we have to use the other equation, force is equal to the integral dF. Now in this case, dF is going to be G times our mass 1, which is our point mass, that particle, times dm, so that little tiny infinitesimal dm, divided by r squared. Okay, so when we insert this into our integral equation above, we get force is equal to this integral, I almost said square root, integral gm1 dm over r squared. Now this r distance here, that is the thing that's changing. So what we need to do here is we need to figure out a way to, instead of having dm here, I need dr here because I want to integrate with respect to r, because again, r is the thing that's changing. So what we do here is we're going to use that linear mass density that we talked about when we derived the rotational inertia of certain objects, if you guys remember that from a couple chapters back. So what we're going to do here, we know that volumetric density, rho, is equal to mass divided by volume. Now similarly, linear mass density is denoted by our lambda, and that is mass divided by the length in this case. Now because this is a uniform rod, which means that it's uniform density, we can equate this to dm over dr. So that small infinitesimal size mass and the little length, that dr, that it takes up. So if I solve this for dm now, dm is going to be equal to big M over big L, so the total mass of the rod divided by the total length of the rod, multiplied by dr, and then so I can take this whole thing and now plug it in up here for that dm in order to get my integral in terms of dr. So I end up getting force is equal to the integral G times mass 1 times big M over big L times r squared, and then that whole thing dr. And then here I can factor out my my constants. So gravitational constant, big G, my mass 1, the mass of the point mass, that's a constant as well. Total mass of the rod is a constant, and total length of the rod is a constant. So what we end up getting here is force is equal to the factoring everything out that I can, G times mass 1 times big M over L times the integral 1 over r squared dr. Now here, we need to find now, before we solve this, we need to find our limits of integration. So our limits of integration here, we're integrating from the beginning of the rod to the end of the rod. So we can see that if we're taking the distance from our mass 1, that's going to be d, and then L plus d is the distance final from mass 1. So initial distance from mass 1 is d, final distance from mass 1 is L plus d. So initial is d, final is L plus d. All right, so now we can finally integrate. 1 over r squared is just r to the negative 2 power, which makes integration a little bit easier. So rewriting this, I get gm1 times m over L. And this is r to the negative 2 power, dr. Of course, when I'm integrating here, I'm adding 1 to that exponent, so the negative 2 becomes a negative 1, and then I'm dividing by that number. So r to the negative 1 power divided by negative 1. I'll write that down so it's less difficult. Divided by negative 1, this becomes negative 1 over r. Okay, so we end up getting force is equal to G times M1 times big M over L, this whole thing here. And then we get our final minus initial. Let me write that down. We're going to negative 1 over R. Then, of course, we're evaluating from D to L plus D. All right, so this becomes GM1 times M over L. And then we get final, which was L plus D, so negative 1 over L plus D, minus initial, which is D, negative 1 over D. And now we can plug in our numbers, finally. So we get force is equal to G times, which is 6.67 times 10 to the negative 11th, times mass 1, which was the mass of the point mass, which is 0.67 kilograms, times the big mass of the rod, which, if I recall, was 5 kilograms, divided by big L, which is the length of the rod, which I think was 3 meters. And then this ends up being a negative 1 over big L, 3 meters, plus our D distance, which was 23 centimeters. So we get 3 plus 0.23 or 3.23 meters. And then plus 1 over D, which was, again, 23 centimeters. But we want that in meters. So for our force, I'm going to do the second part first. I have a negative 1 divided by 3.23, and then I'm adding 1 divided by 0.23. So I get 4.04 for the second part, and then I'm going to multiply that by 6.67 times 10 to the negative 11th times 0.67 times 5, divide everything by 3, and then I end up getting that the force on that point mass from the rod is equal to 3 times 10 to the negative 10th newtons. And there is our answer.